We're going to show how this modeling approach allows us to relate operational drivers that management can influence all the way through to return on capital employed through a series of mathematical relationships. We're going to adopt a top-down hierarchical approach, starting with return on capital employed. We can see in this example we're looking at a copper mine, we're looking at the operation as a whole, and we have a return on capital employed of approximately 15.8%. That's in turn a function of the EBIT and the capital employed itself, which is $2.8 billion. If we mouse over here, we can explicitly see the formula that governs that calculation. Now, if we take EBIT, we can further decompose that into its constituent components, and we can see that that's a function of the saleable pounds of copper, the price of copper in terms of dollars per pound, and the associated unit cost of production of that copper. We can choose to expand on costs, and we can see that those unit costs or total costs are made up of fixed and variable, and in turn we can expand the variable costs into the specific resources and activities, but our main focus for this example will actually be the production side. I will therefore expand the production of copper to its constituent components, and we can see that as expected it's a function of the feed to plant, which is approximately 70 million tons for this period, coming in at a yield of almost 0.5%. That's the combined grade and recovery. Now obviously we can expand the yield into its constituents submodel, but for now our focus will be the actual throughput through the plant and what governs that. So if I expand on that, we can see that it's a function of the value chain itself. And specifically, we have the drilling and blasting activities, loading and hauling, the crushing, and the capability of the plant itself. Now, if I look at drilling and blasting, whilst drilling, for example, is measured in meters, and it does both ore and waste, in this case, we've done various calculations that translate the capability of drilling and blasting to the equivalent tons to plant using a series of mass equivalent factors. So as far as the drilling's capability is concerned, it's doing approximately 90 million tons to plant, and therefore that forms a basis at which, against which its capacity can be compared to the other activities, namely loading and hauling, crushing, and the plant itself. And because all activities have been compared or translated to the equivalent tons to plant, their capacities are comparable. And it's very clear under this context that loading and hauling is a dominant bottleneck within this value chain, where it can do no more than almost 70 million tons, whilst the other activities have significantly more capacity. Given that we have now identified a dominant bottleneck, which is loading and hauling, we're now going to move into applying the same principles of decomposing the underlying value drivers into that activity itself. So if we move on to hauling here, we can see that hauling tons for this period is a function of the operating hours or direct operating hours of the fleet. We have a fleet of 12 trucks. This is on average what each truck is doing in terms of its operating hours, direct operating hours being 33. And if we look at the underlying logic here, we can see that the calendar time is 48 hours, and that gets gradually diluted through maintenance hours, partly planned, partly breakdowns, to give us 34 of 48. There's certain operational delays, standby, etc. That's how we end up with the 33. And across a fleet of 12 trucks, we have 400 hours. And per operating hour, we can in turn decompose our production rate. We can see it's 547 tons per hour, and in turn that's a function of the payload, which is a function of both the capacity of the truck and the fill factor. We can see we're achieving 85% fill factors here, and for each payload it's determined by the number of cycles will determine the production rate, and the number of cycles can be broken down into the cycle time, which is 20 minutes, and the cycle time in turn is broken down into the components of the cycle in terms of travel time, empty and full, the corresponding distance and speed, queuing time, spotting time, etc. By expressing the capability of the hold tons in this way, we can ask the software to answer the question of how we can influence those hold tons by changing one or more of these levers that ultimately drive those hold tons, bearing in mind that the hold tons cannot change in any other way other than changing the specific levers that we can see here. And this specific logic complies with the MECE principle, whereby each lever is mutually exclusive and collectively exhaustive. So if we ask the software to look at how each of those levers influence the hold tons, we will get a sensitivity analysis or tornado chart of this nature, where we have the levers shown down this axis, and for a specific change, 10% in this case, what the impact is on the x-axis shown here. And we can see a hierarchy or sequence of levers, fill factor being quite high up on the list, which is very common of open pit mines, then the respective speeds and so on. Now this sequence is quite interesting because it varies from mine to mine and can vary for each mine over time. Often unplanned maintenance is much higher on the list. Unavailability of labor is also high up on the list, or lost tons due to unavailability of labor, and therefore one can almost recognize a DNA of each mine based on the sequence of the specific drivers. The whole point about this is to make the understanding objective, to create an objective understanding for management between the relationship of how each driver influences the value metric, in this case being tons. Now let's assume we were interested in increasing the tons hauled in this bottleneck activity by actually adding more trucks, and we would do that by creating a new scenario. We would rename it, add more trucks, let's say, and we would come along here and we would add 3 more trucks. We'd go from 12 to 15. We see if we do that, we get approximately 54,000 tons more, assuming we have no adverse or knock-on effects. In other words, every additional truck comes in at 547 tons per hour. Now, if that was true, and we go back to the operation perspective, and we scroll up to the return on capital employed, we can see a massive number. We go from 15% to 27% capital employed on essentially 2.8 billion. Even though we can see our capital employed's gone up a bit because of the purchase of the new trucks, it's a massive increase in ROCE because we're investing in a bottleneck activity. And we can see it's ultimately coming through this massive increase in EBIT. The issue, of course, is the question of whether we're able to harness the full 51,000 tons extra by adding these trucks. The obvious question is there going to be additional queuing time? Is there going to be congestion in the pit, decrease in speed times that will allow this to not manifest? Now we can obviously go into our cycle time and make some assumption around possible increased queuing times. But the truth is we don't know what the queuing time would be. And in the context of a model of this nature, the queuing time is an input. So given the importance of this analysis, we want to take this further, double click on queuing time, and actually build a model that actually models queuing time, and queuing time is an output of that model. So a model of that nature is a discrete event simulation, and we now switch over to discrete event simulation of the load and haul model that actually computes queuing time as an output. So here we move to an actual visualization of a discrete event simulation. A discrete event simulation models the interaction between each object that we're interested in modeling. In this case, trucks and shovels. And we can actually see that the trucks are lining up or spotting against the shovels are loading them up, and the actual queuing or congestion here is modeled explicitly based on the interaction of these objects. And so as a result, as the simulation runs, these outputs are recorded and can then be fed into the value driver tree model that we saw earlier, based on a high fidelity real-time simulation of the nature we're seeing here. So now if we go back to our equation-based value driver tree model, we can see that we had a scenario where we added more trucks, the 3 trucks that gave us the 271,000 tons, and now we're actually going to pull in the simulated scenario for the 15 trucks, where we actually have run the discrete event simulation. And as soon as we do that, we see that we have 255,000 tons instead of the 271,000. And why is that? We can see it's because we're getting a lower tons per hour rate. And we can ask the software to do analysis to explain what happened there in the form of an attribution analysis. And as we do that, we can see that what the software is telling us is if we added the respective number of trucks, we would have got the additional tons that we expected. But we lost tons at the bottom due to queuing at the shovel and the average speed of the trucks going down because of the additional congestion. So these are the knock-on effects that led to fewer tons coming through. So the net result is not 271 but 255,000 because of those knock-on effects. But notwithstanding that, if we go back to the operational perspective, we can see we're still getting a massive increase in our return on capital employed for the operation as a whole, a massive increase in EBIT, and therefore this is a good approach to, or a viable approach to increasing throughput. Now, the key thing to note here is we adopted a top-down approach, and that's quite important because going into every activity into the same amount of detail may not be practical, and therefore this top-down approach guides where the analysis and modeling should provide the necessary detail.